Have you ever looked at some wild physics equation on a chalkboard and just thought to yourself, is that made up? Well, it turns out there's this hidden logic, this secret language that every single formula in the universe has to follow. And today, we're going to learn how to speak it. It's called dimensional analysis. So yeah, how can we be so sure that an equation like E equals mc squared isn't just a random jumble of letters? I mean, what's stopping someone from just writing E equals mc cubed, right? The answer is this incredibly powerful tool that's like the ultimate fact checker for the laws of physics.
You know, to understand any language, you've got to start with the absolute basics, the alphabet. And in the language of physics, our alphabet is made up of these things called physical quantities. They're basically the fundamental building blocks of, well, everything.
To put it simply, a physical quantity is just anything you can measure. That's it. Your height, how much time has passed on the clock, the speed a car is going. These are the concepts that physics uses to actually describe the world around us. If you can't measure it, you can't really talk about it in physics.
Okay, so these quantities, they come in two main flavors. First, you've got base quantities. Think of these as the individual fundamental letters of our alphabet, like M for mass, L for length, and T for time. Then you have the derived quantities, and these are like the words we build using those letters. A great example is speed. Speed isn't fundamental, it's just length divided by time. It's a word we made from the letters L and T.
And believe it or not, this is the entire alphabet. It's surprisingly small. Everything in the entire physical world, from the smallest little particle to the biggest galaxy, can be described using some combination of just these 7 fundamental dimensions. And here's a key thing to remember. A dimension like length is the core idea, while the units we use, like meters or feet or light years, those are just different ways of labeling it. The dimension itself is universal. Okay, so we have our alphabet, but you can't just throw letters together randomly and expect it to make any sense, right? You need grammar. And in physics, the grammar is this one simple but incredibly powerful rule that says how all equations have to behave. This right here is the golden rule. It's called the principle of homogeneity. And really, it's just a fancy way of saying something you already know. You can only add, subtract, or compare things that are the same type of thing. You can add one distance to another distance, sure, but you can't add a distance to a temperature. That just makes no sense. Every single piece of a valid equation has to represent the same kind of physical quantity. All right, let's put this grammar rule to the test. Let's take a really famous equation from kinematics. This formula calculates the distance an object travels, s, based on its initial speed, u, the time, t, and its acceleration, a. So, the big question is, does it follow the rules? Let's translate each part of this equation into our new dimensional language. So s is a distance, that's easy. Its dimension is length, or L. Now the term ut is speed times time. Speed is length per time, so that's L t to the minus 1, and we multiply that by time, t. Then we have the at squared term. Acceleration is length per time squared, or L t to the minus 2, and that gets multiplied by time squared, or t squared. And notice we completely ignore that half. Why? Because pure numbers have no dimension. They're invisible in this language. And now for the really satisfying part. In that ut term, the t to the minus 1 and the t just cancel each other out, leaving us with just L. And look at the at squared term. The t to the minus 2 and the t squared cancel out too, also leaving just L. So what are we left with? L equals L plus L. Every single term in this equation represents a length. The equation is dimensionally correct. It follows the grammar of physics. So this brings us to a really crucial and maybe kind of weird rule you have to get used to. In the world of dimensions, when you add a length to a length, you don't get 2L. You just get length. We're not doing math with numbers here. We're just checking that the type of quantity is consistent. You know, a 5-meter rope plus a 10-meter rope gives you a 15-meter rope, which is still fundamentally a length. Now, checking equations is pretty useful, but what if we could actually build one from scratch? This is where dimensional analysis goes from being a neat trick to an actual superpower. Let's try to derive a physical relationship using nothing but logic. Okay, let's try to figure out the formula for how long it takes a pendulum to make one full swing, its time period, t. We can make a pretty good guess that this time depends on 3 things: the mass of the weight at the end, m, the length of the string, L, and the acceleration due to gravity, g. So we set up an equation. We say that t is proportional to the mass length, and gravity, each raised to some unknown power. Let's just call them z, x, and y for now. Next, we translate all of that into dimensions. On the left side, we have time, which is just t. On the right, we have mass, m to the power of z, length, L to the power of x, and gravity. Well, gravity is an acceleration, so that's length over time squared, or LT-2, all raised to the power of y. Okay, now for the fun part. We just have to make sure the powers for each dimension match on both sides of the equal sign. For mass, m, there's no mass on the left side, so its power is 0. On the right, its power is z, so z must be 0. For time, t, the power on the left is 1. On the right, it's -2y. So 1 has to equal -2y, which means y has to be -1/2. And finally, for length, L, its power on the left is 0. On the right, it's x plus y. Since we just figured out y is -1/2, that means x must be +1/2 to make it all add up to 0. And just like that, the logic gives us the formula. The power for mass is 0, so mass doesn't matter at all. The relationship has to be that t equals some constant, k, times the square root of L over g. I mean, stop and think about what we just did. We didn't swing a single pendulum. We didn't run a single experiment. Just by understanding the grammar of physics, we figured out the fundamental blueprint for how a pendulum has to behave. That is just incredible. Now, as amazing as this tool is, it's not magic. It definitely has some important limitations. It's a sort of reality check that shows us where the pure logic ends and where we have to roll up our sleeves and do some experiments. Remember our awesome pendulum formula? T equals k times the square root of L over g. We figured out almost everything, except for that little k. Our logical derivation gave us this mysterious constant that has no dimensions, but it couldn't tell us what its value is. So what gives? So here's the fine print. Dimensional analysis is completely blind to any numbers that don't have dimensions, like that k or pi or the number 2. It also can't derive equations that involve adding or subtracting different terms, and it gets stuck when you have more complex things like trig functions. It's a fantastic tool for checking if the form of an equation is sound, but it can't generate every little detail out of thin air. And this is where logic meets reality. To figure out the value of k, we actually have to go and do an experiment. And when we do that, we find that for a simple pendulum, that constant k is equal to 2 pi. So you see, dimensional analysis gave us the blueprint, and good old-fashioned experimentation gave us the final critical number. They work together, hand in hand. So now you have this tool. It's like a secret decoder ring for the universe. You can look at any equation in physics and see if it respects the fundamental grammar that holds everything together. You can see the hidden logic. So the only question left is, what equation are you going to check first?